Hey guys, welcome to today's video where we're going to be talking about this little Arduino module I designed. It's a module for doing the GM J1850 variable pulse width protocol with an Arduino. That's kind of the premise of it. It's using this XC68HC IC on here. It's like a little masked ROM microcontroller that was designed to do J1850 out. It's long been obsoleted, but I have a bunch of them. Kind of the genesis of this whole project is the fact that I'm always seeing people talk about and wanting to do little J1850 projects, and there's not a lot of good information out there. There's a ton of different ways to make it using a couple of transistors or using optocouplers and stuff like that, but none of them have very good documentation, while this IC has excellent documentation on it. So I figured for little hobby projects, this is a good thing. There's actually still a ton of these around. I probably have about 100 of these ICs here at my house, and there's sellers on eBay that claim to have 600 of them. So they're around. I wouldn't recommend them for making a product with, which I'm making a product with one, but I wouldn't recommend doing that with them. But they're great for doing little Arduino projects with, which is why I chose to make this module. In this video, we're going to be doing the hardware. I'll do a separate video on the software side of it, but I'm really kind of a hardware guy, so my little Arduino sketch for this isn't really, first of all, it's not really something I actually made. It's something Mike B, who has made a ton of stuff you see on this channel, like IPC Hammer, made, so I can't really take credit for the software either, but we'll definitely take a look at that in a future video. But first, let's assemble one of these, take a look at what's on there and why it's on there. Before we get started on today's video, let's talk about today's sponsor, JLCPCB, who is kind enough to send us our circuit boards and the stencil that we're going to be using in this video. One of the things JLCPCB really wants you to know is that they can do the assembly service for you. This assembly service starts at $8, and I recommend, if you're going to use it, to actually do your design in EasyEDA, so that way you can easily select all the components directly from their basic and extended part catalog. That way you have everything right in the BOM, and it's much easier to integrate this assembly service into your circuit board. That doesn't mean that you have to use it. You can easily use whatever EDA software you choose to use. However, my personal recommendation is to use EasyEDA with it. Okay, so before we really look at the circuit board, let's take a look at this comically oversized stencil I ordered. So that is the PCB. This is all of the stencil. So I made a little test cut here to make sure that my cheap old tin snips will do the job. So yeah, I'm gonna go ahead and trim this up to make it a little bit more manageable. It's still kind of bigger than ideal, but that would be manageable, and it leaves me enough space to trim it down further later down the line. Thankfully, I ordered this stencil to test it out to see if I actually like using a stencil with this circuit board before I went with a panelized version of this circuit board and a stencil for the panel. So I'm glad that I learned that I need to put a custom size in there for JLC PCB from this. I don't know what I was thinking. I guess I just kind of assumed they made a slightly over the size of the circuit board, and they just make it the entire sheet size that you pay for. There is a option that you click to do a custom size, and I just didn't think about it. I didn't do it. So let's just live dangerously and start cutting this thing up. Alright, well, that didn't come out too bad. I was really worried about warping this thing a whole bunch with these tin snips, but it worked out okay. I don't cut a perfect line with them, so I don't think you want to hire me to do any roofing or building the ducts for AC, though. Alright, so let's get an idea of the star of this show, the circuit board and its supporting IC. So, taking a look at this right here, you get an idea of all of the supporting architecture you need for this to work properly, which is why I didn't do a tutorial on using one of these kind of circuit boards that you can just pick up off of eBay or Amazon and soldering it on there and using that, because it's just a little PLCC28 breakout board. And you can definitely go that route to use this. It's just put it on the breakout board and wire it up on a breadboard, and it will work. So some of the things that you do need is a crystal oscillator, and you're going to need the supporting pull-up resistors, pull-down resistors, decoupling capacitors, and the inductor for the output. So that's kind of everything that you need to make it work. You're going to need a 12-volt supply, and you're going to need a 12-volt supply with this board as well. So kind of going from the top to the bottom of the pins here, we have a 5-volt, a 12-volt, a reset, a chip select clock, MOSI, MISO, int, and ground, which that int is an interrupt pin. And so we put this on here, and then it's got all of its supporting architecture that it needs to work. We even have a nice little screw terminal to hook up from the outside world to our connector. So this really is not going to be too bad to assemble. And that's kind of why I got that stencil made, was to try it out for if I wanted to go to more of a production run of it. But we'll see how popular these things are before we really look at scaling up, making more than 5 or 6 of these at a time. So I went with the module style because I prefer modules myself. I did add mounting holes, which you don't always see that on modules, but I wanted that in case somebody actually wanted to implement this into a project that they're going to put into a little project box and put in their car or something. You actually have something to mount it in there with. So you might see in the future I will do a different power supply for people that want to do these kind of projects in their car, where you'll have your automotive power coming in and your 5-volt out, and then a conditioned 12-volt out also. You might see in the future. This is that 5-volt board that I did not that long ago. With this project, it's all open source too, so if you want to just download this and make it yourself, you'll find it on my GitHub, and you'll also have the schematic available to this too. So that way it makes it a little bit easier. So let's actually get into building one of these and get it assembled. Okay, so let's get started with applying our solder paste. And the great thing is we don't actually have to rush with this. We have a couple of hours really until the solder paste will start to dry out after we apply it to the circuit board. So let's make sure this kind of sanded side of it is actually the top side. They kind of sand off the burrs from the laser etching process. So let's get this lined up on here. Let's see. Yeah, that's pretty well lined up there. So now I need to keep it lined up and get the solder paste actually applied to it. So let's go ahead and just put a kind of big old blob of it on there. It's probably way more than I need, but it's okay. Stuff's not very expensive. And we get to start over because I didn't have too much. I actually had too little. Oh, really, I can just go ahead and do it the normal way for those ones that I missed instead of starting over, because we got pretty good application on there, other than these ones I missed right here. So let's go ahead and just do those the normal way. And yeah, I need a little more practice. Oh man, and I had plenty more on here. I just wasn't getting it down there. Oh well. Alright, and that should get this circuit board assembled here. So we'll start with the smaller stuff and then do the bigger stuff last. That's kind of how I like to work when I'm assembling a circuit board. From here on out, I'll probably just fast forward through. Y'all seen me do assembly before. Okay, so that's it for the surface mount technology, or the SMT components on there. As you can see, I got way too excessive on the solder that I hand dispensed versus that stencil. Everything was really perfect. This footprint that I used here is a little bit oversized, but I thought I used the same footprint on a different design. The legs themselves are properly spaced apart here, but they're just quite a bit longer than they need to be. So, maybe I used the wrong footprint, but it does fit, so that's good. Let's go ahead and get the inductor on here and some of the other components too. And there we go. That is a fully assembled module. So we have our PLCC chip soldered on here. We have all of our passive components on and our through-hole components installed. So pretty simple to assemble. I went with the male header on here. I actually designed this in mind with using a female header instead, which you can't see, but that's the BOM. So this was really kind of the intended header to be used on here, which will let you plug in the male wires in, but this one lets you just set it on the circuit board. So this will work for what I want to do. So the reason why I was thinking about using the female one is that way if you mount this in something, you have easy access to run your female wires up there. Obviously, you could just solder wires in if that was a concern on here, though. Okay, well, I figured out why that crystal looked wrong. I did grab the wrong bag of components. I knew this footprint worked right for this component because I used it on a different board, and this is just something I copied off of another project I'm working on. But, yeah, so that's what happens when you grab the wrong bag of components. They're wrong. So I accidentally put an 8 megahertz crystal on here that I use in a lot of my STM32 stuff, and I meant to put on this 4 megahertz crystal. This runs at 4 megahertz. Look at how much more appropriately that fits on those pads there. So, wrong component. I didn't figure it out by powering it up. I just kept looking at it and was like, this just does not look right. So, there we go. We got the right one on there. Okay, so here is the wired up module. What we are looking at here on this breadboard is an Arduino Nano, the module we just assembled, and a little buck converter so that way I don't have to use 2 power sources. The reason why we need this is because this chip needs 2 voltages to run. It needs 12 volts and it needs 5 volts. This guy needs 5 volts to run, and so I just have 12 in right here because our test fixture is also going to be running 12 volts. The reason why this needs 12 volts is because this bus right here actually runs at around 7 volts. It has a wake signal that's higher if I'm not mistaken, but we're not really going to get into the nitty gritty of J1850 in here. We're just going to get into using this module with an Arduino. So it is kind of a spaghetti mess here of wiring. But to simplify it here, what we're looking at is the reset pin of our module goes to pin 8, our chip select goes to pin 10, our MOSI goes to pin 11, our MISO goes to pin 12, and our clock goes to pin 13. And these are all based off of exactly how it's labeled on here. We also like I said, have the 12 volts, and then it goes into this buck converter, comes out 5 volts, and that 5 volts powers both our Arduino and the module. We have our ground pin going to ground, and our 5 volt going to the 5 volt rail right here. Our 12 volts is coming from a regulated DC power supply, and it goes to both this and our instrument cluster here that we're going to be using in just a moment to test the module. Okay, so now let's take a quick look at it actually operating. So what we're going to be sending is 3 different commands to it. We're going to send it a command to sweep all the gauges. We're going to send it a command to turn on all of the air lights, and one to turn on all the little blocks this display. This display might be a little bit hard to see, especially because I'm running it at 12 volts instead of 14 volts. Okay, and that is it cycling. You may have noticed that the check engine light didn't come on. That is because that light's actually not commanded by the bus. It's commanded by its own wire that comes directly from the PCM. So that is one thing to be aware of with that command, is it doesn't turn on that particular air light. Okay, I know I said this wasn't going to be a software video, but let's take a quick glance in Arduino and check out what's going on in the sketch, because this is going to be linked in the GitHub for this, that way you guys can get started if you buy one of these modules or decide to recreate it. Now, I can't take credit for all this. Most of this was written by Mike B. I cleaned it up a little bit of how I like it written, but he's the one that figured out how to really communicate with this chip, not me, because I couldn't make heads or tails of a lot of that data sheet. It is pretty vague on some of the details. So let's go ahead and take a look at what's going on here. So this first cycle that you see, so there's this void dot SPI cycle that I have going on right here. What this is when you want to send a command or something to the actual chip of what's going on. So that's what this void is that it keeps calling to, because it sends it in 2-byte packets to it. So that's all what it does, is it's just, hey, here's these 2 bytes. So you go, okay, we got first byte and second byte, and we're going to send them. So we can do like a SPI cycle and then call these 2. So this one is like a setup command to just set up the little chip to get it ready to go. Down here is where we actually start sending it some real commands. So I kind of wrote this out so you get an understanding of what exactly it's doing there. It sends a byte of the frame of like what we're going to send, and a command byte to the chip, so that way the chip knows what to do with it. So this would be our first byte of our frame, and then this would be a command saying, hey, we're going to send this, store it, and then this is the second byte, and this is, hey, we're going to send another byte behind it. And then we get all the way down here, and this is, okay, this is the last byte, send it. So that's kind of what's going on right there. And then we just have a delay, and we do it again for the other command. And see, this one is the sweeps all the gauges. So this is the J1850 frame, which we have a priority, a destination, a source, a command, a subcommand, and then just data. And then that's how this one's set up too, and that one as well. So that's really everything going on in the sketch. It's a pretty simple sketch, not a whole lot going on. We don't need any special drivers to talk to this thing. It's just SPI communication, and we can just send it like this. So I find this a simple, logical way, easy to follow manner of doing this, and you're welcome to do it however you feel like, though. Okay, so one thing to mention about this is I haven't figured out how to read back with them yet. It's capable of doing it, and there's instructions in the data sheet on how to do it. However, it's kind of as clear as mud in there on how to do it, so it's going to take a little while. Mike and I are both working on that right now. I don't know if we'll get it figured out anytime soon, though, because we both have other projects and a life going on. So just something to be aware of there is right now it can write data, it can't read it back from the bus. It can't possibly be that hard. It's more of just a matter of testing and doing it. So I need to build a second one of these for myself, so that way I can send data from one to the other, and then I can receive it and get it all figured out on how it's doing that. So that's kind of the where this is. It's still a work in progress. So yes, I am going to sell these. I'm going to have them listed on my eBay account just because that's what I have set up right now. Eventually, I'll set up a 10D account to sell stuff like this. But for now, it's just easiest to stick with eBay. I know eBay kind of sucks, but oh well. I'll kind of get over it, pay my fee, and get it. So yeah, they're going to be $35, and you absolutely can build them much cheaper yourself. So if the $35 is kind of a sticker shock for you, you're more than welcome to download the files, get it produced yourself, and order the parts. So I just wanted to make that option available for people to buy one of these if they don't want to assemble them themselves, because I know not everybody likes to do hardware like I do. Most people prefer to do the software side of things. So yeah, I hope you guys enjoyed the video, and I will see you guys in the next one.